Welcome to my CS179F final project, specifically on vulnerability 2018-533 in the Linux kernel. This was a presentation given about 2 weeks before this recording with my partner Donovan Coleman, but he is not here for the video, so we will have to do without him. So, specifically, the nature of the vulnerability is that it was patched on the 3rd of January 2018 and by one Mohammed Ghanem, and it affects the Ubuntu kernel 16.04 or Linux kernels 14.8 and 14.4. It specifically relates to the reliable datagram socket module, where there is a null pointer dereference in a corrupt system call, which is you can give the kernel a corrupt parameter, which will cause this null pointer dereference. The reliable datagram socket was introduced in June of 2009 and specifically relates to transporting datagram data structures between computers and can be found in data centers and in servers that use it, which may not be data centers. It's not loaded in by default, but you can find it in the by installing the package and then mod probing it or sudo insmod. So specifically what happens with a null pointer dereference is that the standard response is a kernel oops. A kernel oops comes from a philosophy that a working system is easier to debug than a dead one. We don't want to outright crash the system if it's still recoverable, so we just output a message to the log and then kill the offending progress. You can consider this like a sig-seg-v for kernel programmers, at least in Linux. And this happens with null pointer dereferences in this context, since that is the vulnerability. And the this is an image of a null pointer dereference log, unable to handle kernel null pointer at page mapping, etc. And then it gives the ID of the oops, which is 0 in this case. So specifically for this vulnerability, it happens with the RDS send message function. What happens is that when you call the send message syscall, you get to RDS send message at line 1022 of send.c, which will call RDS control message atomic. And this is where the corruption happens. So if we move forward, we get to RDS control message atomic, and we arrive at the user provided local address. However, if we do not byte align it, then we will just we will go to the error and then return. However, note that we do not scatter set page, which will mean that if we ever use the opsg function to get a page, it will still be null. Then when we leave and we return to RDS send message, it's assuming that we ran properly. And then here we go to message put, message purge, and we never properly set op active to false either. So we will enter atomic free op, we'll try to free it. And then within it, we will set the page dirty, except the page is null. We go here to get a mapping. We run all the way down until we get to page dereference compound head, which is a null pointer dereference, which is the final vulnerability. Whoa. Now specifically, the patch is to add a false flag for the op active whenever we error. And then this is specifically the call trace if we were to run the vulnerability. We get the send message, we run all the way to the bind, and then here we get to RDS send message, RDS message put, atomic free, and set page dirty, and we don't get the rest of them because the rest of the functions are inline, in my understanding, and not visible to the debugger. So this is fairly harmless as a vulnerability, unless you can map the 0 virtual address, you can't really do much other than crash the program. Or if you run it sufficiently enough, the kernel might be like, hey, we've reached too many oopses. This might be a bad situation. Let's crash. All right. But otherwise, it's not very harmful. However, of course, if we can inject code at 0 in the virtual address, we may be potentially able to gain access to information or gain access to privilege escalation. And that's what we will get to with the exploit presentation. Now that I've talked about the first part of this vulnerability, that is 2018-5333, a null pointer dereference in the RDS module, I will get to the second part, which is how we use it to exploit the system and gain a local privilege escalation. So, this involves another vulnerability, that is 2019-9213, which will be, which is a grows down memory stack has a error in error checking or mistake in error checking, which allows the stack to map farther than the minimum address that the kernel sets, which allows us to gain access to that 0 virtual memory address in the first page of a program. So a bit of background before I continue further. C organizes structs by aligning them to, I'm not sure if the term is word aligned or byte aligned, but there's always some padding if it does not align perfectly. That is, if you have a char only uses 1 byte to notify a character, but it does not specifically align with the rest of the struct. So there will be a padding of 3 bytes so that we can then go to the next address down and put our 4 or our int of size 4 in the next address. And it may not be a next address, it may just be further along in the same address, but there's always some padding, which is important to note for the rest of the part. We can consider it sort of like a gigantic array, but we'll get to that part when there's the explanation of the return-oriented programming. So this is the control flow of the program, and I'll just briefly go over it. So first, we have to bypass the Castler defense, which is the kernel address space level randomization, meaning if we're looking for a function within kernel space, there's going to be some random offset to it, which we'll need to account for. But since this vulnerability does not relate to Castler, we can just assume that this is successfully completed. Then we map the null address to gain access to the 0 address, or we map the first table to gain access to the null address. Then we prepare a fake stack, feed the shell and credential function into the fake stack, as well as inject the fake stack into exchange ESP, which is a kernel function which exchanges the stack pointer of the kernel with the user, or in this case with our fake stack, which we specify. And then we trigger the null pointer dereference and then dereference the function pointer, which is to exchange ESP. That switches the kernel stack. The kernel then assumes that this fake stack is its own and executes our shell credential function. So the first part of this is mapping the null address, or mapping the first table, because in all programs, the first page is never allocated, so that a page fault will detect a null pointer dereference and properly kernel oops, as we saw in the first presentation. Here, this function utilizes the LD-debug environment variable to print a string into the addresses from 10,000 to 0. So I'll just walk through this function. So we map a grows down stack at 10,000 because it has to be above the minimum address the kernel sets, otherwise we'll get an error. Then we open the file a file which is proc self-mem. Then we use the LD debug to write this help message into the file that we have seeked at 10,000 and then progressively further down. So there's a lot to unpack here. First, proc self mem is a tool for programs to write into unwritable memory. Then we should note that every step of the function, we go from we move down 1,000, we seek the file down 1,000 in hex, and then we write. So this will progressively write into the page until we reach 0. We will be writing it to 0, but C doesn't allow us to printf 0 because it has some checks in it itself. But if we print, for example, the 1,000, which is in that first page of the program, we get this message, which is it is working properly. The next part of this is preparing a fake stack. So exchange ESP, the function itself, is expecting a proper, or it's not expecting it, but we have to give it the proper stack so that it doesn't error. So this requires us aligning our fake stack along this offset or mask, and then we have to get some offsets, but not specific to our needs. We then feed the shell function or credential function, the credential and then the shell function to our fake stack so that when the kernel runs this, it will first prepare a 0 credential, which stands for kernel credential or root credential. Then we commit those creds to our process, which will then make the process escalate in privilege, and then we swap to the user, which will then run this shell, which will give us the shell. So when before we get to the details of the return-oriented programming, we must go back to CVE 2018, which is the null pointer dereference. So this is the actual bug. So we just need a RDS socket. Then we need to get or feed it a local address which is corrupt, and that will cause the null pointer dereference. So otherwise, usually we would get a do page fault. Then we would get here, and then we'd say, hey, there's no context to this. This is null and unable to handle kernel paging request at virtual address 0, and that is the log that we saw before. And then I just added this part in here to say that whenever we're touching the null or we're touching an unallocated memory, it will try to expand the stack if it has the map grows down. And that's what was happening with map null. Every time we were touching, which is important, we need to touch the memory so that it allocates some for us. This is where it will expand the stack. Here, injecting the stack, this is the return-oriented programming, and there's going to be a lot to unpack here. So basically, this is just a reminder of how, this is just a reminder on how the Linux organizes a process. Or a program. So first we have the program here, we have our stack, our heap, some uninitialized data, initialized data, and then some text or code, although sometimes they organize code up here. So in a virtual address, the kernel is always after this address, just so that we consider the kernel is never a separate program. It's always part of the program, but accessing it requires superior user mode or super user. And then, of course, here, this 0, these pages are never actually allocated because we're trying to make sure that whenever there is a page fault, we catch it down here. So that if we ever try to dereference null, there's an error. So specifically, this is the code in the exploit, and here just to note, we have address result, which goes into 1, and we have the exchange ESP function pointer, which goes into 3. So what is happening here? Well, we have to organize code here so that we, when we dereference null, there's a struct member offsets that will grab result, go to then 0, and then go to 0, and then go to the struct member offset, which is exchange ESP. So specifically, that looks like this. There's a lot to unpack. I know I wasn't great with these slides, but once again, this is the code. We put the address of result into 1 and exchange ESP into 3. So what happens? We can find this code in the 2018 version of the Linux on mmPageWriteBack.c 2005-41 line. And so this is setPageDirty. So what happens is that there's a setPageDirty function pointer that we grab from address operations. So specifically, when we get to mapping, the page is null. So what happens is the mapping, specifically here, will go to 1. And so 1 is the address of result. Then we dereference result, getting null. And then from null, which is back to 0, or in this case, from null, we go back to 0. And then we get the offset of setPageDirty, which in this case is 3. So here we go, this is null. We get the mapping, which is the result. Then we go to address ops, and we get setPageDirty, which is 3, which then is our exchange ESP, and later on it runs this function, which will actually be our exchange ESP function, switch it out, and that is our exploit. The only part of this that I didn't totally understand was for address space, why the address of result then dereferences to null. But in this case, I imagine there's a lot of offsets, and so this is what happens when we set to the address of result. But in any case, this is what happens with our exploit. And then the next part will be the present or the demo of the exploit. Welcome to the demo of CVE 2018-5333. So here I have the exploit.c open, and here is the specific trigger bug function, which has the local address exploitation. Now, to note, this is not my exploit. This is an exploit provided by bcools on GitHub, which I have copied here. I did not create this. I'm not good enough yet to create this exploit. But in any case, this is the exploit itself. So here's the trigger bug, or the null pointer dereference trigger. This is the map null here. And then as we go down, there's some extra information, which I won't get into the details on, all the way down till we find main. So here is the shell function. So it just system shell. Or otherwise. Here we have a bunch of extra stuff, but on the details we bypass KSLR, then we get these function pointers, we map the fake stack, prepare the fake stack, and then execute the payload with map null being right here. So if I save this, then I exit out, then I open the terminal, cd desktop, clear gcc-o exploit./exploit.c. It's made, and we run it. Of course, we haven't loaded RDS kernel module because this is not a server that uses RDS. This is a normal desktop. So I will be right back once I have loaded that in. So I have just now loaded the RDS module, and so this should work. Ta-da! So the exploit functions, just as explained, where it loads a kernel version, or just detects it, then checks the system, maps null, bypasses Castler. These are interchangeable. And then gets the specific commit creds, prepare kernel cred, and exchange ESP function pointers, maps the fake stack, then executes the payload, which will switch, and then we get the root. So in this case, I will just do who am I root. That's about it. And then don't upgrade. Okay, and then exit. Who am I? I'm VBox user. And that has been the demo on CVE 2018-5333. And that concludes my presentation on this vulnerability of the Linux kernel. Of course, this vulnerability has already been patched and no longer exists. But on any system that is older than 2018, this is a runnable exploit. However, like it's been said, you will need to have the RDS module loaded in. Once again, I do not claim responsibility on any actions you take. So if you suddenly get in trouble because you use this exploit on some old server, it's not my fault, y'all. This is just a presentation on the details.